Welcome and welcome again to this course on CFD. Today is our second module of this week. So far we have done detailed description about different interpolation scheme available to obtain variable at phase for using it in convection term. We have listed 5 different scheme: central difference type, that is otherwise linear interpolation scheme, pure upwinding, power law scheme, hybrid scheme and quick scheme. We also took an illustration and explained performance by central difference type scheme as well as pure upwinding scheme. In today's class we will particularly see performance by quick scheme for the same illustration. For the sake of completeness, we will list all the scheme information. For CD and pure upwind approximation, the generic formula is AP pi p equal to AW phi W plus AE phi E. In the case of CD scheme, coefficients AW, AE and AP are listed as shown, and you can recognize AP, that is a point of interest coefficient, is a summation of neighboring coefficients, that is AW plus AE plus additional term. For pure upwind, again AW, AE and AP are listed, and for the sake of direction convenience and to write down one generic formula, a condition is imposed, a condition is included in the coefficient as shown here. For example, AW is written here as FDW plus max of FCW comma 0, which means if the flow direction is from left to right, then it is positive with respect to the coordinate direction, then max of this condition will result in considering FCW. Similarly for the other coefficient, and as observed in CD scheme, AP is again summation of neighboring coefficient plus additional term. For quick scheme, we have similar term, that is AW phi W plus AE phi E plus one extra node on the upstream side, which is again considering both the side possibility. The generic formula is given here. So, the final formula is AP pi p equal to AW phi W plus AE phi E plus AEE phi EE, which is east of east, plus AWW plus phi WW, which is west of west. As usual, the node interest coefficient AP is related to neighboring nodes. So, AP equal to AW plus AE plus AEE plus AWW and an additional term. Now, let us look at the coefficients in detail: AW, AWW, AE and AEE. Again this formula has a generic condition incorporated here by including a coefficient beta. For beta equal to 1, FCW is greater than 0, that means the flow is from left to right, then it will take accordingly the coefficient value. Similarly, for beta less equal to 0 or FCW less than 0, the flow is from right to left, mostly in the case of reverse flow, then it will take appropriately. So, this generic formula is suitable for any direction, similarly for pure upwinding. So, this helps while writing the code, it automatically switches based on the flow velocity condition. Now, let us look at this problem statement once again. For the figure shown below, solve by convection diffusion finite volume formulation. So, in this figure there is a convection as well as diffusion for the problem. Boundary condition is defined on one side, on the left side at x is equal to 0, phi equal to 1, then boundary condition on the other side, right side at x is equal to L, phi is equal to 0. Now, the flow is from left to right hence it is only positive. So, in the generic coefficient it will be considered accordingly. We mentioned just to consider performance by different scheme as well as to understand influence of mesh and velocity condition, solve the problem by different approximation scheme CD, pure up-wind, quick, solve the problem for very low velocity u is equal to 0.1 meters per second and a high velocity of 2.5 meters per second. So, the difference in velocity will decide the weightage of convection term in the case of pure upwinding or hybrid scheme. Similarly, solve it with 5 equally spaced mesh points or 20 equally spaced mesh point. So, the given domain length is x is equal to 0 to x is equal to L, length L. If L is equal to 1, then if you divide by 5 equally spaced mesh point, delta x will be 0.02. If you divide by 20, then delta x will be 0.02, and this delta x term goes into the diffusion term calculation. In the last slide, we explained the problem. Now, let us get some more explanation. 1D domain with the boundary condition phi at 0 equal to 1, phi at L equal to 0 when x is equal to L is now discretized with 5 equally spaced cell, and for the problem define rho is taken to be 1.0 kg per meter cube and gamma taken to be 0.1 kg meter per second. Let us take two cases, and this is a domain. We have discretized the domain with 5 equal nodal points 1, 2, 3, 4, 5, and they are equally spaced. So, you see delta x as the distance between node 1 and 2, same way the distance between node 2 and 3 and so on. Because it is equally spaced, node 1 which is a node near to the left boundary, similarly node 5 which is a node near to the right boundary, both are at a distance of delta x by 2 with respect to the respective boundary, and boundary conditions is already shown here both on left side as well as on the right side. And for this problem analytical solution is already given, and that is what is displayed here. Now, we take one of the case, that is u equal to 0.1 meters per second and 5 mesh points. We calculate convective flux as well as diffusive flux. Convective flux equal to rho into u, rho is already defined as 1 kg per meter cube and u is 0.1 meters per second. So, rho u you will get 0.1. Similarly, for diffusive flux it is defined as gamma by delta x, gamma is 0.1, delta x is 0.2 and that is equal to 0.5. We want to evaluate convective flux as well as diffusive flux to get an idea of role of convective flux and diffusive flux. Now, this relation or weightage between convective flux and diffusive flux will inform or tell us about performance by different discretization scheme. We know quick scheme illustration as shown here. This is given particularly for this illustration problem where the flow is only in one direction, that is from left to right, and that is what you are seeing here. Both UW as well as UE are shown from left to right. So, for the phase W, phi W is your interest, phi small case letter w is your interest. Then you have a quadratic fit running through 3 nodes. So, immediate downstream node is phi at P, then one node on the left is phi at W capital letter, then one node upstream is phi WW, that is a quadratic fit. Similarly, for phase UE, then you consider one node immediately downstream is phi at capital letter E, then one node on the other side is phi at P, then one more node immediately upstream is phi at W. That is the graphical representation of quadratic fit. Now, we write down the generic formula phi at any phase is as shown here. As I already mentioned, in this formula note the letter subscript I represent immediate downstream, then I minus 1 and I minus 2 are upstream. The CD approximation to evaluate delta phi at CV phases for diffusive flux is used, because in this problem we have convection term as well as diffusion term, and diffusion term we mentioned we will use only central difference type approximation, and we already did that in detail. Now again for this problem area is the same, so AE is equal to AW. Now we are using quick scheme approximation for the evaluation of variable at the phase. Now after doing that operation and putting in both in the final discretized form, then you will get in the regular form final discretized equation as shown here. AP is equal to AW plus AE plus AE plus AWW plus remaining term, and phi AP phi P is related to neighboring coefficient as shown here, and we already listed this AW, AWW, AE and AEE. In this problem the flow is only from left to right, so accordingly the coefficients are taken only suiting to this problem, and beta is defined as we did before. Now we apply this generic formula for each node separately. As we mentioned while describing the problem figure, node 1 and node 5 are near boundary nodes. Internal nodes are 2, 3, 4. So 2, 3, 4 nodes will have the same expression, and that is what is shown here in this table 2, 3, 4. Then you evaluate, then you get this. For 1 and 5 they are boundary nodes, and we have already explained the left side of the boundary node 1 and the right side of the boundary node 5 actually the boundary condition, then accordingly you write down the expression, coefficient expression. Now we have to substitute values that is given in the problem statement in terms of rho, gamma, velocity as well as number of mesh points that you have considered. So if you substitute those values in this flux calculation properly, so for example FDW means diffusion flux at west phase, similarly diffusion flux at L and so on. You substitute all those values, then for this condition u is equal to 2 meters 0.2 meters per second, then you evaluate and you get this coefficients actually calculated. So for node 1 as well as node 5 you have a source term coming from the boundary condition, and for node 2 which is near next to the near boundary, and that will have again a west of west, because in this problem the flow is from left to right. When you write down for node 2, then quick formula will have AP, AW and AWW. AWW which is west of west, and in this problem it happens to be the boundary condition phase. So that will also appear as a source term, and that is what is shown here as SP and SU. Node 3 and 4 is actually deep inside and they do not have the boundary condition incorporation. So SU and SP will take the value of 0. So these numbers are obtained after substituting problem statement value, that is u is equal to 0.2 meters per second delta x based on the condition that 5 mesh points are used, gamma is already given, rho is given. Then if you substitute in the generic formula and take appropriately the boundary condition, then you are able to evaluate and get these values. Now this needs to be put in the form of a matrix, so that is what you will see here. So in the form of a matrix it is shown, there is one coefficient matrix, then there is one unknown column vector, and that is equal to another known column vector. So in this phi 1 to phi are nodal values to be determined, and corresponding coefficients are written in this adjacent coefficient matrix. As I explained before, if you look at this matrix particularly, you have one diagonal element. So, in this case it is 2.175, 1.075, 1.075, 1.075 and 1.925. These are all elements along the diagonal. Then you have immediately super diagonal, then there is one immediately subdiagonal. So, that is the tridiagonal matrix structure, but for this problem when you use quick scheme you get additional element. So, the tridiagonality matrix structure is actually disturbed. This also we explained before. Now, we are seeing it actually with the problem and corresponding numerical values. So, there is a procedure to invert this matrix. We will reserve that matrix inversion procedure for next class. So, once you do this matrix inversion you are able to get answer or unknown variable values phi 1 to phi 5. Now, we already mentioned there is a analytical solution available and you can make a comparison. Now, this is comparison on the performance for the same problem, but using a different value of u 0.1 meters per second. Okay. The previous slide I showed values corresponding to 0.2 meters per second and this is slightly lesser 0.1 meters per second, but everything else same, that is 5 mesh points rho and gamma. And you see here performance quick scheme plot and exact analytical solution plot they are shown, and in this case one exactly matches with the other and that is why you are seeing only one color. And you can cross check the left boundary, it is already given as 1 and the right boundary it is 0 and there are 5 nodal points 1, 2, 3, 4, 5. So, you are able to compare and you see performance because it is so low velocity quick scheme performs equally well. In the next plot you see performance of the quick scheme. If you increase the velocity from 0.1 meters per second to 2.5 meters per second, number of mesh points still remains as 5, then you see the performance of the quick scheme. So, this color, the red color one is exact solution, whereas the quick scheme starts showing wiggle from node 3, node 4, node 5 and then there is a right boundary. This is because you are having a 5 mesh points and delta x is 0.2 and you compare convection is 2.5 and diffusion is 0.5 and performance of quick scheme is poor. Now, we will see in the next slide same flow condition, that is 2.5 meters per second. Instead of 5 mesh points for the same domain, increase it to 20 mesh points. Okay. And again rho u the value remains because it is function of velocity and density, it is 2.5, whereas diffusion is changed gamma by delta x from 0.1 by 0.05 is equal to 2.0. So, diffusion is now 2.0, which is almost of the same order as a convection. 2.0 is the diffusion flux and 2.5 is a convection flux. Now, you see the performance of the quick scheme for the same problem, the results obtained are better and it is very close to the solution obtained by quick scheme. So, this plot tells you how important it is, though the scheme is correct, if you increase the mesh size then you are getting a better solution or correct solution. So, it is necessary to check all the parameters before coming to the decision whether scheme is good or flow condition is not properly imposed. We have seen a similar one last class when we demonstrated CD scheme. Similarly, when we use 5 mesh points for higher velocity, the CD scheme was showing a wiggle, that is oscillation, and when we changed from 5 mesh points to 20 mesh point, solution improved. Okay. Now, in this slide I am going to make comparison of all the schemes. First one is comparison for the flow condition u is equal to 0.1 meters per second. This flow is very low velocity, hence the scheme is not much influenced. Even if you use 5 node points, you see here performance by all the scheme almost matches with the exact solution and there is not much difference. Now, if I increase the velocity from 0.1 meters per second to 2.5 meters per second, you can see the comparison for the same 5 nodes. You can see here exact solution is marked by this color, then up in scheme is marked by red color, and you have a quick scheme, and then this is quick scheme, and then you have a central difference scheme. You can make interpretation with this plot itself. Up in scheme is almost matching with exact solution, and then central difference scheme showing a very big variation or very big wiggle, whereas quick scheme, when you use a quick scheme, though the performance is not matching, you are able to see the wiggle gets reduced, right. From central difference scheme it gets reduced this much. Similarly, on the other side it gets reduced from this side to this level, and you can understand quick scheme is a kind of combination of CD as well as pure upwinding that we already mentioned when we explained quick scheme. It has 2 nodes on either side plus 1 node on the upstream side. So, 2 nodes on the either side behaves like a CD, and 1 extra node on the upstream side behaves like a pure upwinding. So, it has an influence of pure upwinding as well as CD scheme. That information is very well captured in this comparison illustration. The performance by quick scheme is better, though it is not good, but the wiggle gets reduced and it is getting closer to the solution, and this much reduction you can interpret it is because of the pure upwinding type introduced in the quick scheme. And if you increase the mesh size for the same problem from 5 to 20, then all the schemes behaves very well, then all are able to compare results or exact solution. So, in this lecture, last few classes, we have seen in detail finite volume formulation for convection and diffusion terms in Navier-Stokes equation. We also learned how to do near boundary implementation. We learned there is a need to do different approximation to get the variable value on the phase. We learned 5 difference scheme. We also learned the performance by taking one illustration, and by increasing the mesh size or by increasing the flow condition, performance differs. Most part of the lectures on this finite volume formulations are adopted from book The Finite Volume Method authored by Versteeg and Malala-Shekhar. So, next class we are going to see another interesting topic. Until then, have fun. Thank you.